Greetings again, Geography 306, Weather and Climate. This is the second of two videos for Unit 1, Module 2. And so we're going to take a look at the structure of the atmosphere, in specific how what the pressure looks like, essentially, as we move from Earth toward space, and then what the temperature looks like. There are some very distinct temperature layers that become important in our study. So we start off with pressure. And what is atmospheric pressure? It's the weight or the force of the air pushing on something, on you and me, on the ground, on a cloud. And the key thing to understand, as shown by this graphic, is as we move from the surface of the Earth toward space, pressure continuously decreases. Now, why does it decrease? It decreases because the density of the molecules decrease, how tightly packed they are together. So if you look at this little tiny picture here, this is supposed to be a representation of what the molecules would look like if I stacked them all up in a column toward space. So a chunk this big, I'm just circling it, however big that is, look at how tightly packed the molecules are. That's high density and high pressure. If we go way out here, a look at the molecules aren't packed as tightly. So that would be lower density and lower pressure. On this graphic here, you can see essentially the same thing. So this is pressure as measured in something called millibars. There's a number of different units that we can use to measure pressure. And at sea level, essentially closest to the surface of the Earth, pressure is just a little over 1,000 millibars. Now, if you look at your notes, another way to measure this is in pounds per square inch, 14.7 pounds per square inch. Another classic unit is 1 kilogram per square centimeter. Now, a square centimeter is about the area of my pinky fingernail. 2 kilograms is a little over 2 pounds. What that means is there's a little over 2 pounds pushing on every bit of surface that is 1 square centimeter. So these numbers will continue to make more sense as we go along. Remember, those values are measurements for average sea level pressure. What happens when we go towards space? We already said pressure decreases. So this red line shows just how rapidly it decreases. Notice that by the time I get to just 2 miles above Earth's surface, it's already dropped to, what is that? About 650 millibars. By the time I get to 8 miles, it's dropped to 200 millibars, a fifth of its pressure. And by the time I get out to a little over 20 miles, it's dropped to virtually nothing, virtually no pressure, because there's virtually no air left. In other words, the air is incredibly thin by the time I've gotten that far out towards space. Now, having said that, the atmosphere, if I put a round number on it, you see this is 22 miles. The atmosphere generally goes to about 300 miles, 500 kilometers tall. By the time you get that far out, there's virtually no air at all. There might be a molecule here, and then 10 yards away, there's another molecule. That's not much air. So that should give you a general sense of the pressure, the structure of pressure as we move from Earth toward space. And one of the things I didn't say is that the air is held by gravity. So gravity is what is helping pull these molecules down toward the surface of the Earth. Why are they thicker as we're closer to the Earth? Because the gravity is stronger the closer you are to Earth. So really important to consider this pattern. Atmospheric pressure is highest at Earth's surface and decreases toward space. Why? Because the density of the air is highest at Earth's surface and decreases toward space. So again, remember those values: average sea level pressure, a little over 1,000 millibars at sea level, or 14.7 pounds per square inch, or not written on here, but 1 kilogram per square centimeter. So then we take a look at temperature, and what you see here are the four major temperature layers of the atmosphere: troposphere, stratosphere, mesosphere, thermosphere. The dividing boundaries between each of them, once you get to the top of the troposphere, they call it the tropopause, because there's a sudden pause in the pattern of temperature that you've been experiencing, that somebody has been experiencing. What do we call the top of the stratosphere? The stratopause. What do we call the top of the mesosphere? The mesopause, and so forth. Now, we're going to start with and mostly stick with the troposphere. That is the most important layer to us. And you see this red line tracks the changes in temperature, the average temperature, as you move upward through the atmosphere. So what do we notice if you start at Earth's surface, which is right here? What happens as we go upward to the temperature on this graph? You see it drops way off. It suddenly gets much, much colder. And then as we move into the stratosphere, it gets warmer, and then there's a pause. And as we move through the mesosphere, it gets colder, and then there's a pause. And as we move through the thermosphere, it gets warmer. So again, returning to the troposphere. In your notes, make sure you know where this is and you see this. So what is it about the troposphere? Why are we so concerned about the troposphere? Well, it's first of all, it's where we live. It's where humans exist. It is the layer at the surface of Earth, and it goes out to about 8 miles or so. It depends on whether you're toward the North Pole or the South Pole or closer to the equator. My notes give you some much more specific numbers. But why it's important to us is, again, it's where humans live, and it's where most of the air is. Like 90% of all of the air, considering remember, it's thick, it's high density down here, 90% of the air exists in this layer. And this is where all of our weather takes place. So mostly in our class, we're concerned with this layer called the troposphere. And the fact that temperature decreases on average as we move up toward this layer called the tropopause is incredibly important. That fact is really important. And this is referred to as the normal lapse rate, the average temperature decrease with an increase in altitude above Earth's surface. The average temperature decrease as you increase in altitude above Earth's surface. Normal is a word that means average. Lapse means to lessen or to decrease. Rate means change over distance in this case. So 6.5 Celsius degrees per 1,000 meters, or 3.5 Fahrenheit degrees per 1,000 feet. And this one is very common for people to know in the United States because we use these units. And this is pretty much what you experience if you go up into the mountains. At some point during the winter in California, you reach a line where you hit snow. Well, what we know is it gets colder as we progressively go into the mountains. Why does it get colder? Because mountains poke up into this cold air. Mountains, literally, we think of them as bumps that are poking up into that cold air. Why is it so much colder up there? Well, this is a longer story, but let me just tell you, the troposphere is basically heated by Earth. A lot of people think the sun heats the air. Turns out the sun pretty much has to heat Earth, and then Earth heats the air. So where's the warmest air going to be? Closest to the source of heat. That's a really short version, but that should help you understand why it's warmest at the surface in this layer. And it gets colder and colder and colder as we go up, because as you go up, you're moving away from the source of heat. So those mountains, like this picture of a mountain here, poke up into that cold air. And we use the term normal lapse rate to describe how fast the temperature decreases. Notice you see this term tropopause. What is the tropopause? Well, it's really the elevation at which that temperature decrease begins to slow down and stop and reverse itself. So that's why they call it a pause. Now, for a minute, I'm going to take a little side detour, and in your notes, it talks about calculating some of these values. The normal lapse rate, as I said, is an average. But what somebody can do at any given time, what people who work for the National Weather Service in the United States do all the time, is send up weather balloons. And you send up a weather balloon with an instrument on it called a radiosonde, and it collects data. Well, one of the big things it does is it collects temperature. So, as I said, the normal lapse rate is the average. What is the environmental lapse rate? It is the actual observed rate of temperature decrease at a given place and time. Every day in Northern California, there's a weather balloon sent up in Alameda near Oakland, and they collect the data for our area. And they might come back and they might say, oh, the environmental lapse rate for today in Alameda is only 2.5 Fahrenheit degrees per 1,000 feet. Or maybe they'll say it's 5.2 Fahrenheit degrees per 1,000 feet. They're going to calculate an exact number. Boy, this number is important to understand whether we're going to have cloud formation or fog, all sorts of things. So that is the environmental lapse rate, the actual observed rate of temperature decrease at a given place and time as you move away from Earth's surface. So just remember, these two terms are very similar, but really the way to think about it is you might need to take hundreds and hundreds and hundreds of environmental lapse rate readings in order to take an average and get the normal lapse rate reading. So I'm going to, in the slides, walk you through how to make some of these calculations. So if here's a weather balloon, and there's extra videos that describe a lot of these things. There's an extra video about ozone we talked about earlier. There is an extra video about launching weather balloons and how that's done. And so here's the little instrument package, radiosonde. And they will fill up this weather balloon, send it upward, and let it float upward, and then they will eventually retrieve the data. So here is just an example. If the temperature was 20 degrees Celsius when the radiosonde was launched, 20 is just a comfortable, it's like right around 70 Fahrenheit. And then the temperature is 0 Celsius, that's freezing of water, after rising 4,000 meters. What is the environmental lapse rate? How can I calculate the environmental lapse rate? So suddenly I find out that my weather balloon went up to 4,000 meters and it was freezing, but it started out at 20 Celsius. How can I calculate the environmental lapse rate? Okay, so here is your formula, which is the same formula that I've given you here in your notes. Keep that in mind. So 20 temperature decrease was 20 Celsius. How much did it decrease? It went from 20 to 0. So that's a decrease of 20 divided by the elevation difference. How did I get 4,000? Well, it says we rose 4,000 meters, so that's your difference. I could have told you that that we started at 0 meters sea level and then rose to 4,000. That's the same thing. You take the difference. The difference between 0 and 4,000 is 4,000. And so that one's not that hard. You just run the math through. Remember, you got to multiply it by 1,000 at the end because the value is per 1,000 feet. So 5 Celsius degrees per 1,000 feet. I should be able to give you these basic numbers and you should be able to calculate that on an exam. So let's do another one. A little bit harder. If the temperature was 17 Celsius when the radiosonde was launched, what is the temperature likely to be when it reaches 1,000 meters above the surface? So now this is a slightly different question. I didn't ask you what the environmental lapse rate was. I am asking you to tell me what the temperature is once we get to 1,000 meters. So what do? Use the normal lapse rate when you are not given the environmental lapse rate. So if you don't know, just use the average. So in this case, how do you get your final temp? That's what we're trying to calculate. Take your starting temp, that was 17. Take your elevational difference, I said we rose 1,000 meters, and you multiply it by the normal lapse rate. This was right in your notes as the normal lapse rate. So 17 minus, and in this case, here's a quick mathematical trick. If you just cancel the 3 zeros and the meters, What do you get? You get 17 minus 1 times 6.5, which is 17 minus 6.5, which is 10.5 Celsius. So in other words, we started at 17 Celsius and it cooled off by that much, and it ended up being that temperature. One more real quick, if the temperature, these are in English units, was 40 Fahrenheit at 2,000 meters elevation, what is the temperature likely to be if you hike to the top of the mountain at 6,000 feet elevation? So again, you'll use the normal lapse rate, but this time you'll use the English units. So final temp equals starting temp minus elevation difference times normal lapse rate. So 40 minus 4,000 times 3.5 per thousand. And I showed you before, you can cancel the zeros in this case. So what do you get? 40 minus the value of 4 times 3.5. That's 40 minus 14, which is 26 degrees Fahrenheit. So you should be able to run through these if I give you simple versions of these calculations. Okay, so what about the other layers in the atmosphere? We're less concerned with these, although they are important, so we'll keep that in mind. But we're going to run through them a little more quickly. So the stratosphere is the layer above the troposphere, and it's roughly 8 miles to about 30 miles. And what we see is the temperature begins to increase in that layer. So in the troposphere, it drops, then it pauses and it goes back up. That's primarily because of this is where the ozone lives, and ozone absorbs ultraviolet radiation, which warms things up. And so then what about, and let me make something clear is, again, later we're going to talk about ozone pollution at Earth's surface. This is natural ozone. This is the good ozone, or some people call it the stratospheric ozone. They're the same gas. That's the tough thing, but I want you to separate the concepts, because one is naturally occurring and really good for us, and one is caused and made by humans and can be really damaging for humans. So, of course, once you get to the top of the stratosphere, they refer to that as stratopause. What's happening there? Suddenly the temperature is dropping off significantly, and that's partly because we no longer have any ozone up there. This layer is called the mesosphere, so the temperature gets much, much colder, and we're not going to spend much time or concern about the mesosphere. But remember, as we go up, there's less and less air. And then finally, we get to the mesopause out at about 50 miles, 80 kilometers. And then above this layer, we have what is referred to as the thermosphere, and it can get extremely hot in the thermosphere, temperatures of over 1,000 Celsius. And what's happening in the thermosphere is it's really absorbing a lot of the sun's most intense shortwave damaging radiation. We talk about gamma rays, cosmic rays, X-rays, and when the atmosphere, remember there's only a very little bit of it, but that which is there absorbs that incredibly high energy solar radiation. Fortunately, it absorbs it because we don't want it to arrive down to us. It gets absorbed and stuck up there. And when radiation gets absorbed, it converts to heat. It gets really hot. So as I said, it's like 1,000 Celsius, 1,800 Fahrenheit. That's like 4 times you can get your oven. But it turns out that if you somehow were there, it wouldn't burn you. You'd need a spacesuit, hopefully, but it wouldn't burn you because there's so much distance between the molecules. The temperature would be a lot, but when you don't have much substance, you can have a really, really hot molecule, but if you only have one molecule, it doesn't really have enough heat to burn you. So that's a weird thing, is the temperature can be really hot, but if there's not much substance, if there's not much air, even though that air is super hot, then it's not going to give off a lot of heat. So you see here the aurora I'm not going to get heavily into it except to say that in some cases, the energy or the atmosphere gets so incredibly superheated from this high energy radiation from the sun that it actually glows under certain circumstances. And that's called the aurora borealis in the far northern hemisphere toward the North Pole, or the aurora australis in the far southern hemisphere toward Antarctica. And it's really, it's an artifact of that layer of the atmosphere absorbing this super intense radiation from the sun. Let me say that specifically that layer is referred to as the ionosphere, and you can read this little comment about the ionosphere and how it leads to this glowing layer of atmosphere under certain circumstances. So that wraps up our very first section of notes. We took this section and turned it into 2 modules. Most sections of notes will only be 1 module worth. And please notice there are sample multiple choice questions. You should go through those. I give you answers to those, and I give you possible essay questions. So whenever you see these, you can assume that I will take from these, and that is partly how I build my exams. So you should start working on those and assembling those answers. All right, thanks for your valuable time. And that is the second of 2 videos. All right, thank you.